Hi, and welcome to Module 12. In Module 11, we were discussing formal notions of computational complexity. And earlier we had discussed rates of growth, and the complexity when it comes to computation demonstrates in a formal way whether a function grows in terms of its resource consumption, its runtime, at least as quickly as another function asymptotically, or maybe it grows not faster than another function g of n, or maybe our function f of n grows asymptotically just as fast as this other function of g of n. So different notions of rate of growth. And now, if we can look at a function and analyze what complexity it's in, it can provide us some rules of thumb in how to select algorithms, but not always. So as always, there are trade-offs, and the devil is in the details, and we need to choose things carefully. But let's see where we are. So let's begin by some examples of low complexity algorithms. An algorithm that's theta of 1, that means that we have a few lines of code, that they're very simple. Each of them runs on our computer. It's 2-3 instructions. That's it. So if we have a few simple lines of codes, no function calls, nothing fancy, no square root of the number where we don't really know the resolution of the number, nothing surprising, theta of 1. That really means constant. As far as we're concerned, could be a nanosecond, could be a year, but no matter how big the size of the problem, it'll always run the same. Theta of log n. An example would be searching for an element in a balanced tree data structure. We're going to learn about these data structures soon. So in the data structure, which has n elements, if we arrange them in a tree, these n elements, and the tree is balanced, every leaf of the tree is going to appear at depth approximately log n, and searching in the tree is going to be a search from the root of the tree until we hit a leaf, and that takes theta of log of n operations. Another example is theta of square root of n. If we have a very large number and we want to identify whether it's prime or not, an example of when this is useful would be when we are looking at cryptography, and we want to see whether a number is a prime, because if it is a prime, that may be helpful, or maybe not. Bottom line, we need to evaluate all the numbers 1, 2, 3, 4 up to square root of n, and if we have ruled out that none of them divide n evenly, then we know that it's a prime. So these are low complexity algorithms. Another class would be medium complexity, theta of n. We have n numbers, we want to find the minimum or the maximum. N log n. We've chatted about sorting. We had the insert sort, which was n squared, and in contrast, the merge sort is n log n. Similarly, a fast Fourier transform, f of t, is n log n, whereas a discrete Fourier transform is n squared. Another example of theta of n squared is a matrix vector product. So just to make this clear, we'll have a matrix, and we'll be multiplying it by a vector. The vector will be a column vector of length n. Similarly, the matrix will be of dimension n by n, and every number in the output, so let's say this number, is equal to an inner product of the corresponding row in the matrix with the column vector. And this inner product means that we're taking corresponding pairs that appear in the same order in the column and the row. We're multiplying the pair, and then we're adding up all the pairs. So we basically have, for each of the numbers at the output, we have n products, we have n minus 1 additions, and then we have operations for looking stuff up in the matrix, looking stuff up in the column vector, and so on. So each of the outputs take theta of n time, and because we have n locations at the output, that's theta of n squared. Okay, so theta of n, linear in n, quadratic in n, and cubic in n would be an example of matrix inversion, or matrix-matrix product. That's another example. Okay. What about a high complexity? So recall, low complexity was sublinear, very sublinear. I'm not talking about like theta of n to the power of 0.99. Theta of n squared, unless n is truly huge, you know, in the 10 to the 20 range, theta of n squared is typically reasonable. Then we have polynomial in n, linear, quadratic, cubic, and we have much worse than that, exponential. One example would be, what if we need to optimally decode n bits in a communication system? So we got n numbers, and we want to consider which of the sets of n bits, 2 to the n such sets, correspond well to those numbers. And for each of those numbers, we need to calculate something. Maybe it's a log likelihood or something else, some score. And we're going to optimize that score among all to the 2 to the n possibilities. So overall, theta of 2 to the power of n times f of n. And of course, typically the f of n would be something small, perhaps linear in n or something like that. Typically, the 2 to the n dominates here. Another example of a high complexity algorithm would be when we need to process all the permutations of n objects. Permutations, the number of permutations of n objects is n factorial. N factorial is even larger than a constant to the power of n. So const to the power of n is little o of n to the n. And the reason for that is that, or rather, it's little o of n factorial, which itself is little o of n to the power of n. Because what is n factorial? N factorial can be shown to be something like n divided by e to the power of n, and there might be a square root of n in here, and there might be a 2 pi, you know. I'm just putting a question mark, but it's basically n divided by e to the power of n with correction terms that are no more than linear in n. And n divided by e to the power of n is clearly less than n to the power of n, because we're dividing by e to the n. And on the other hand, it's clearly more than any constant to the power of n, because n to the power of n dominates the constant. So high complexity, medium complexity, low complexity. So at this time you may think, hey, how do we select a better algorithm? Well, if two algorithms have a quite different complexity, we choose the lower one. This is obvious. If you can choose between the FFT and the standard discrete Fourier transform computation, you run the FFT, unless you happen to know that your problem size is always going to be very low. Or if you have a merge sort versus an insertion sort, you're going to choose the merge sort. But what if the complexities are similar? Are you going to choose the fast one, the slow one, or maybe it depends? So let me illustrate with a counterexample that shows that it depends. And if you don't have drastically different complexity, this requires some care. So here's something that I worked on around 2005. Suffix sorting is used in some data compression algorithms, and there are different algorithms to implement suffix sorting. So when I'm talking about different implementations, by implementation, I don't mean not different code, but different algorithms, okay? And these algorithms may have different computational complexities. Now the previous approaches, which often you'll see in a paper, it's called the prior art. Now, why do scientists call these things art? It's because at the frontiers of knowledge, knowledge is not exactly defined. Where there's uncertainty, where it's not obvious even to experts, it's starting to be less of a well-defined science and more of an art. So the prior art means in terms of what's out there, the existing knowledge, but pushing the frontier. So suffix trees are one algorithm for suffix sorting. and their worst case is linear. The bad part about suffix trees is that in practice, they're slow. So they're linear, but with a bad constant. And in practice, the fastest methods, their average case was linear. They had a good constant, but the worst case was quadratic. And in fact, again, this was during my PhD, I had an example text file, which we ran the suffix sorting on, and it wasn't too big. It was like 800 kilobytes. In the big picture of things, not a large file, definitely not in the big data era. And the fastest method required almost an hour. And recall, that method was actually, in most cases, quite fast. In most cases, it was maybe 5 times faster than suffix trees. But for this example, the suffix trees ran in 4 or 5 seconds. So on the one hand, 99.9% of the time, the suffix trees were slower, but their worst case was better. So then we proposed a new algorithm, which appears in this paper. And this algorithm was a new suffix sorting algorithm. Its computational complexity was theta of n square root of log of n. So now let's recall where we were. We had theta of n, and theta of n is definitely less than or equal to, so it is big O of n square root of log n, which in turn is definitely better than theta of n squared. Now let's also think, what is the square root of log of n? So let's take n, and let's take the log of n, and let's take the square root. And to keep it simple, let's do log base 2, okay? So if n is 2, the logarithm is 1, and the square root is 1. That's easy. Let's take 4. The logarithm is 2, and the square root of 2 is something like 1.41. What about, well, okay, so 4 didn't move us much. What about, let's say, 16? The logarithm of 16 is 4, and the square root of 4 is 2. So yeah, I mean, 2 is better than 4. Okay, but let's continue this. Let's move to larger numbers. 1,000. So we know that the log of 1,000 is approximately 10, and we know that the square root of 10 is approximately 3.1. Okay, so now we're starting to see that 3.1 is not a large number. Let's say 1,000,000. Approximately 20, and the square root is approximately 4.5. Now 1,000,000 is starting to be, it's not a big file, but it's getting there. And what about 1,000,000,000? Now in the big data era of 2020, 1,000,000,000 may not be a really big file. It's pretty big. But it's maybe not big data yet. Big data probably means that it doesn't fit on a thumb drive. But a gigabyte was certainly big data in 2005, okay? Or rather, maybe it wasn't massive data, but it was hard to store. Log of 1,000,000,000 is 30, and the square root would be something like 5.5. Now, what I'm trying to show here, compare 5.5 to 1,000,000,000. So the 5.5, the n square root of log n is way, way, way closer to n. Much, much smaller than n squared. So we have a function that's faster than suffix trees in practice because the square root of log n is small. It was about 2 times faster. And recall that we had another algorithm that was maybe another factor of 2 times faster on average, but it had a bad worst case. So what we were showing in that paper is that our worst case was barely worse than linear. Now, of course, you'll always have theoretical computer scientists that from their perspective, n square root of log n is not as good as n, but you can see that practically speaking, even take a trillion, log of a trillion is approximately 40, and the square root of that is maybe, let's say, 6.3. So practically speaking, we can say that unless you're compressing the entire internet, in which case, the number might be, I don't know, 7 or 8, practically speaking, the number is always going to be manageable. So the worst case is reasonable, and practically speaking, it was about 2 times faster than suffix trees. And the real point here is that constants matter unless the computational complexity is quite different. And the word quite is suggesting that you need to be judicious here. If we give you an n squared versus an n, unless you happen to know that these are very small problems, of course you're going to go with the n, but yeah, you need to be judicious. So that'll be it. And we'll continue next time.